We'll continue with calorimetry, and now we'll talk about a different kind of calorimetry, which is constant volume calorimetry, which is also called as bomb calorimetry. So what is a bomb calorimeter? This is the same technique of calorimetry where we measure the heat transfer that is occurring in a process. Only difference here is that this is a constant volume calorimeter, which means it is done in a container which has a fixed volume. This is also known as bomb calorimeter because this calorimeter can handle very high pressures and very high temperature. So most of the reaction that require very high temperature or very high pressure conditions, those are usually conducted in these kind of calorimeters known as bomb calorimeter. Okay, it can withstand very high temperatures and pressure changes, and it is basically sealed and insulated from the surroundings. So again, heat cannot transfer outside of the calorimeter, and this type of calorimeter, bomb calorimeter, is more similar to an isolated system. Okay, so the constant pressure calorimeter is more like a open system, and this type of calorimeter is very similar to an isolated system. So what is the major difference when it comes to calculations using a bomb calorimeter? The major difference is, in this case, we use the total heat capacity of the calorimeter instead of using the specific heat capacity of water. So previously in the normal calorimetry, constant pressure, we were using Q is equal to Q calorimeter is equal to mass of calorimeter, which was water, C of water, and delta T of water, because everything was water. In the bomb calorimeter, we do not use water specifically, we use a combined heat capacity for different components of calorimeter. So here the Q calorimeter is equal to actually C calorimeter times delta T. So we do not use mass here, we use C calorimeter, which is basically just a combination of all of this. Okay, so instead of using MC, we use C, capital C calorimeter. This capital C is specific to every bomb calorimeter. Everything else still stays the same. So just how if we are doing a reaction in a bomb calorimeter, if I do a chemical reaction here, then the heat that is lost by the reaction, negative, is equal to the heat gained by the calorimeter. It is the same system. So Q calorimeter is negative Q of reaction or solution if the reaction is being done in solution form, and this heat of the reaction is also equal to delta E of the reaction. Because this is constant volume, we call it E of the reaction instead of enthalpy, but it is the same as heat that is involved in a reaction. Questions would look something like this. When 1.010 grams of sucrose undergoes combustion in a bomb calorimeter, the temperature rises from 24.9 degrees Celsius to 28.9 degrees Celsius. Find delta E of the reaction for combustion of sucrose in kilojoules per mole. The heat capacity of the calorimeter is given to us 4.90. So what's given to us is, this is the mass of sucrose, this is the initial temperature, and this is the final temperature of the calorimeter. Question is asking what is delta E of the reaction. The unit is given to us kilojoules per mole, and heat capacity is given, which is capital C calorimeter. The other questions in constant pressure, what's given to us is specific heat capacity. Okay, that is small c, this is capital C. So the major difference here is, when we are working with a bomb calorimeter, always remember the Q of calorimeter is equal to negative Q of your reaction. Okay, so I am interested in delta E, which is basically equal to delta E of your reaction. Okay, or let's put it in this manner, Q of calorimeter is equal to negative Q of the reaction, which means I can say that Q of my reaction, which is I'm interested in, is equal to negative Q of calorimeter, and the Q of reaction is going to be equal to delta E of my reaction, which means I can see delta E of my reaction is equal to negative Q of calorimeter. So if I can find Q of calorimeter, that's my answer. What is Q of calorimeter? Because it is a bomb calorimeter, it is not going to be MCAT. mc delta t, it is going to be capital C calorimeter times delta t. Capital C is given to us right here. Delta t we can find. Delta t will be T final minus T initial, which is going to be 28.33 minus 24.92. That value goes here. That is delta T. From there I can find what is E of my reaction. Once we know E of reaction, the unit the question is asking is in kilojoules per mole. So I have to divide this. The answer that we get here is going to be kilojoules from here, because the unit is kilojoules. So the answer will be kilojoules, but I need kilojoules per mole, so we will divide it by moles. That would give us kilojoules delta E of reaction divided by moles would give me kilojoules per mole. So for that I need to find moles. What's given to us is grams of sucrose, so we will convert grams of sucrose into moles. How will we do that? For that we need molar mass. Grams will be converted into moles using molar mass, right? So 1 mole is equal to molar mass of the substance. So moving on, we can try another question, very similar. A 1 gram sample of decane is ignited. So this is the mass of decane, 1 gram, inside a bomb calorimeter. The temperature rises from 20 to 78 degrees Celsius. 20 is initial, it rises to 78, so that's final temperature. Given that the heat capacity of calorimeter is this, determine E of the reaction in kilojoules per mole. So it's the same approach. This is C of calorimeter. Question is asking what is E of reaction, which is going to be heat of the reaction over moles, kilojoules per mole. How can I find heat of the reaction? Heat of the reaction is going to be negative heat of calorimeter, which is going to be negative C times delta T. So C goes here, delta T final minus initial will go here. From this I can find Q of reaction. Q of reaction goes in this formula, and mass can be converted into moles using molar mass. And once we have moles, that will go here and we can get our delta E of reaction. So it's the same approach as shown, negative 47.6, find the moles, divide, get the ratio, that is our kilojoules per mole. Let's try another type of example question. Burning 1 mole of methane CH4 in a calorimeter warms 10 kg of water by 21.3 degrees Celsius. Calculate the heat produced in this combustion process. Given the specific heat capacity of water is this. So let's see what's given to us. Question says when 1 mole of methane was burned, it warmed up 10 kgs of water. So this is mass of water by this much degree Celsius. So that's delta T for water. Change of temperature. Question is asking what is the heat produced in this process. So question is asking what is the heat of this reaction when C of water is given to us. Okay, remember what is heat of the reaction? This is a normal calorimeter, it doesn't specify it's a bomb, so that is going to be mc delta T. Okay, sorry, before that, what is the heat of the reaction? Heat of the reaction is going to be equal to negative Q of calorimeter. And what is Q of calorimeter? That is going to be mass of water, C of water, delta T of water. I just skipped this step right away. But basically, your Q of reaction is equal to this. Mass of water is given to us 10 kg. Okay, but what's the difference? If we look at units, this is in kg, whereas C is in grams, which means, remember, you always have to have your mass in grams here. So if we convert 10 kgs into grams, that would be 10.0 times 10 raised to power 3 grams times 4.184 joules per gram degree Celsius times delta T is 21.3 degree Celsius. Degree Celsius, gram, gone. Your final answer is in joules. Okay, what is important to remember here? Please remember that if the question is talking about normal calorimeter, which is it just specifies calorimeter, constant pressure, it means Q of calorimeter is mc delta T. If the question specifies bomb calorimeter, then Q of calorimeter is capital C of calorimeter times delta T. That is the major difference between two types of questions. Rest, everything else is same. One loses, the other one gains the heat. And Q of reaction is always going to be, that does not change. Q of reaction is negative Q of calorimeter. Here also Q of reaction is negative Q of calorimeter. If the unit says joules per mole, you just find the moles and divide by that. Okay. The next concept is, how is heat related to stoichiometry? Heat can be related to stoichiometry, which means if a reaction is occurring when the more reactants are used, the larger would be the change in the enthalpy. For example, if this is a reaction, C3H8 plus 5O2 gives us 3 CO2 and 4 water. And the heat of the reaction, the enthalpy of the reaction is negative 2044 kilojoules. That simply means that based on stoichiometry, how many moles of C3H8 are we using? We are using 1 mole of C3H8. We are using 5 moles of oxygen. We are releasing or producing 3 moles of CO2 and 4 moles of water, which means when 1 mole of C3H8 burns with 5 moles of oxygen and produces 3 moles of CO2 and 4 moles of water, the heat of the reaction is negative 2044 kilojoules, which simply means for every 1 mole of C3H8, the heat is negative 2044 kilojoules. So if you ever need a relationship, a conversion factor between moles of a substance and heat, you get it from the chemical reaction. For 5 moles of oxygen, the heat is negative 2044. For 3 moles of CO2, the heat is negative 2044 kilojoules. For 4 moles of water, the heat is negative 2044 kilojoules, which simply means if instead of 1 mole, let's say I want to do 2 moles of C3H8, the amount of heat is going to be 2 times negative 2044 kilojoules, because this heat is for 1 mole. So if I do 2 moles of reactant, the heat would be twice, which simply means if I multiply this reaction by 6, by 10, let's say, if I do this reaction 10 times, then how much heat would be released? The heat would also become 10 times. Okay, that is heat with stoichiometry. You can relate any moles with any amount of heat. I can relate it with moles, which means I can also relate it with grams. For example, if I say 5 moles of oxygen releases this much heat, how much heat would be released by, let's say, 34 grams of oxygen? Okay, so 34 grams, what is my relationship? I know for every 5 moles of oxygen, the heat is 2044 kilojoules. So if I know how many moles of oxygen I have, I can convert grams of oxygen into moles of oxygen. If I know moles of oxygen, I can use this conversion factor and convert it into the heat that is released by oxygen, right? How can I convert grams to moles? Using molar mass. We know 1 mole of oxygen is 32.00 grams of oxygen. From here we find moles. Once I know moles, I use this conversion factor, converted into heat in kilojoules. So you can relate stoichiometry with heat by using a balanced chemical reaction. Kind of like this. Question. Consider the following thermochemical equation. 2A gives AA. Delta H is negative 51 joules. What is the heat associated with the reaction of 6 moles of A? So the question is, if I have 6 moles of A, what would be the heat? Okay, so moles of A, heat is what the question is asking. What is my conversion factor between moles and heat here? For 2 moles of A, the heat is 51.0 joules, which means if I start with 6 moles of A, multiply it with the conversion factor, my starting unit is moles of A, so I divide by moles of A. How many moles of A from here? 2. Negative 51.0 joules. Moles of A go on. My final answer is joules, which would be 6 times 51, which basically gives you 153, negative 153 joules. 6 times 51 divided by 2. Okay, negative, that means C is my answer. So you can relate heat with number of moles. Example like this. Water can be formed via the reaction of gaseous hydrogen and oxygen. This is the reaction. Delta H for this reaction is given to us. Delta H is minus 572 kilojoules per mole. Determine the enthalpy of the reaction in units of kilojoules per mole of water produced. Okay, so if this is the reaction, for this reaction, delta H is negative 572. Question is asking what is the delta H for water that is produced in kilojoules per mole. So I need the moles of water here, kilojoules per mole. When you look at this reaction, what does delta H mean? It means for producing 2 moles of water, heat is negative 572 kilojoules. Whenever in a chemical reaction you see delta H, that means it says for 2 moles of hydrogen, this is stoichiometry and thermochemistry. Okay, so for 2 moles of hydrogen gas, how much heat is released? Negative 572. For 1 mole of oxygen, same amount of heat is released. For 2 moles of water, this much heat is released. The question is asking what is delta H for per mole. So I would divide it by 2. My conversion factor is for every 2 moles of water, the amount of heat that is produced is negative 572 kilojoules. So if I want kilojoules per mole, that is going to be negative 572 kilojoules divided by 2 moles. That would give me my heat per mole. That is it. Okay, so we divide this by 2. Important thing from this question to remember is that you can relate stoichiometry with heat of the enthalpy of the reaction as well. So this means 2 moles of hydrogen, this much heat, 1 mole of oxygen, this much heat, 2 moles of water, this much heat. Now if the question says what is the heat released for 10 moles of water? Okay, for 2 moles it is 572. For 10 moles, that means I have 5 times the number of moles. The heat is also going to be 5 times. So this basically tells you that thermochemistry can be related to stoichiometry. Okay, example like this. The equation and the enthalpy for the combustion of methane, CH4, is given to us. Delta H for this reaction is negative 891 kilojoules for this reaction. Okay, which means for 1 mole of methane it is this much heat, for 2 oxygen it is this much heat, for 1 CO2 this much heat, for 2 water this much heat. So now the question can relate any of these reactants or products with heat. This equation gives us our relationship. Determine the amount of heat produced by the combustion of 3.3 moles of methane. What is my conversion factor? The question says I have 3.30 moles of this, and it's asking what is the heat that is produced. My conversion factor between moles and heat is, for every 1 mole of CH4, I need to go here. What's given to me is moles of CH4. So I need a relationship between moles of CH4 and heat. For every 1 mole of CH4 from the balanced equation, how much heat is released? 891 kilojoules. So if I have 3.30 moles of CH4, we multiply it with a conversion factor. Because my starting unit is mole of CH4, who goes in the bottom? Mole of CH4, which is 1 from here. 1 mole of CH4, negative 891 kilojoules. Mole of CH4 gone, which means my answer would be negative 891.3.30 kilojoules of heat. If we plug this into calculator, we get 2940.3 kilojoules. That is how much heat is released in this process. Okay, this is 3 sig figs, this is also 3 sig figs, so my final answer should be 3, which will be 2940 kilojoules. So you can relate moles, grams, anything to heat. How? Through the enthalpy of the reaction. Remember that 1 mole, this much heat. Okay, 2 moles of oxygen, this much heat. Now the question is, determine the enthalpy for the following equation. What is the following equation? It's 2 CH4, 4 oxygen, 2 CO2, 4 water. If you pay attention to the reaction that's given to us, I have 1 CH4. This is 2 CH4. I have 2 oxygen here. This is 4 oxygen. I have 1 CO2 here, 2 CO2 here, 2 water here, 4 water here, which means everything is doubled. That simply means I am performing this top reaction 2 times. If I do this top reaction 2 times, that gives me this reaction, which means how much heat will be released? Heat is going to be also 2 times of what it was earlier. That is it. So stoichiometry can be related to heat as well. So your final answer is going to be 2 times of the top reaction, which is 1780 kilojoules.